Okay, in this additional experience, I have prepared a number of labels, and yes, the idea is to work through them and try to associate them to some of the minerals. Maybe I will look at some other specimens in here if I don't find the mineral of interest, but let's see what we can achieve in terms of linking names with the respective mineralogy. I think I will start with quartz, and I will try to illustrate you some of the features that lead me to associate a particular label or name, or essentially name minerals. So quartz, I have a couple of examples here, and the main way I distinguish quartz is really the translucency. It's very glassy, and its hardness. So it's quite hard, 7, and I know that this is the amethyst variety of quartz, which is has this characteristic purple color. So certainly quartz is one mineral that is relatively easy to recognize because of the hardness and the glassy nature. We can take a similar mineral, which is fluorite. I can recognize fluorite because it's more greenish. So they say when you look through fluorite, it's like looking through seawater. And in fact, I can see some deep green inside the crystal. And that's another important diagnostic feature. So certainly fluorite can be recognized for that, but also because its hardness, it's characteristically less. So I think it's on the order of 4. We can test that because we should be able to scratch it with the knife. And in fact, I can do it. I actually broke the crystal. So I can scratch it with a knife, and you cannot scratch quartz with a knife. And it's kind of possible also to scratch with this, but I cannot scratch it, I think, with the copper coin. So I think it's 4, which will be the carbonate. So let's take calcite, and so we pick some examples of calcite based on what we were considering earlier. So the calcite is very translucent. The difference really, if it's euhedral, will be that it looks as a shifted cube. So it's like you are moving the faces of the cube in opposite directions, and that gives you this characteristic tilting, and essentially a rhomboedral geometry. It's not always like that, so you might have other circumstances in which the crystals don't look the same, but you can use hardness as well as reactivity to hydrochloric acid as an indication of calcite. And we had also these other crystals here, so the translucency is variable. This crystal is not as translucent as the others, but still you can see the characteristic cleavages. So I can see at least 3 cleavages in this crystal, which can be also useful for the discrimination of calcite. On the same color, I would have the calcium sulfate. So we have chalk here, much softer, very similar to talc. In fact, you can use it on the board, you know. So it's quite easy to recognize, also because of the luster. It's incredibly dull, so it doesn't really reflect any light. And it stays on your fingers. Similarly to talc, so we could also include the talc here. So that's talc. And then we have, so I've talked about talc before, so I don't think it's necessary to add much more. I would compare also in terms of hardness talc to gypsum. So remember, this doesn't react to HCl, so we can definitely distinguish this from calcite, which could be confused because of the cleavages and the symmetry for this particular crystal. I have to find gypsum, which I don't see. Let's see if I can find it later, but I'll put it there temporarily. We can look at the other phyllosilicates. Take these, which is the muscovite and biotite. So one thing we didn't do is to check for the streak. Another key diagnostic feature for these two minerals, which are phyllosilicates, is to check the streak color. And so you can see here the streak color is really light brown for the biotite. The biotite is quite black, so you will be able to differentiate biotite based on the streak color sometimes. It does have a single cleavage, remember that, and it's quite soft, but not as soft as talc. If I use the same approach with muscovite, I get a white to greenish streak. In this case, it looks quite white. Try different parts of the crystal to make sure the streak is quite white in this case. So that's a diagnostic feature for muscovite. Muscovite also, if you remove a flake of muscovite, which I think I had before here, yes, so a small flake of muscovite will be highly transparent, so I can see through the muscovite quite easily. So muscovite, we have muscovite here, and the biotite, which is this one here. Gypsum, I found it, now it's this one, and we can move on to the others. Other soft mineral is talc or serpentine, so this will be your serpentine, and it's characteristically greenish alteration of basalt or other ultramafic rocks as peridotites, and so this goes well with the olivine as well. So we have olivine here, which is greenish, but much harder if compared to serpentine. And serpentine, let's see if I can find it. There we go. We have the serpentine here. I'm using these names because of my pronunciation of the different minerals, so hopefully you can read them through the camera, and that will help you understand the correct name for each mineral. I will leave this off and look at other things that I can see here. This one is still biotite, I can definitely say that. Or maybe not, maybe it's muscovite. So again, streak color can help me with this distinction. And definitely looks white, so I would put it in here as muscovite. And then look at other minerals. We are left with these pinkish minerals and this one that is quite translucent. So this one, you can recognize it because it's a cubic mineral. So the angle between the faces will be 90 degrees, and it's also salty to the taste. So that's halite. You can see also the way it fractures, and so it does have cleavages that resemble the cubic cleavage, and it's a bit greasy to the touch, so definitely quite easy to recognize based on salty taste and the fact that it's a cubic compound. So halite should be somewhere in here, hopefully. There we go, and we can place it here. So that's my specimen of halite. So very transparent, pretty much like calcite, but the salty taste, it's also quite easy to break, so the hardness is very low as well, probably less than calcite. Then we have the feldspar. So this is K feldspar. 3 examples. You can recognize feldspar because of this characteristic pinkish color, which will be critical also for the classification of igneous rocks. So usually alkali granites contain a good amount of feldspar, or K feldspar, so potassium feldspar essentially. So that's a silicate that is really abundant on the crust, so heavily present in granitic rocks, as I was saying, and you can recognize the cleavage on this, as well as the Carlsbad twinning, which is often found in a high temperature feldspar like sanidine, and that will help you with the identification of feldspar that is alkali feldspar. So this is kind of distinct from plagioclase, which is quite often more whitish in color. But yeah, this is K feldspar, and so its hardness is part of the Mohs scale, and it will be 6. So orthoclase is also another terminology that you can use to describe the variety of feldspar. So orthoclase is the potassium-rich feldspar. Okay, then we have other things like the sulfur, so native sulfur. So sulfur is somewhere in here probably, or maybe not, we might miss it. It doesn't matter. We have really talked about these quite a bit. So remember this lemony yellow color, the fact that it's not really hard that much, so we can scratch it, I think, with a copper coin. All those aspects can be helpful in recognizing sulfur. And what else can we find here? This we didn't talk about it, but probably we can leave it for later. I would finish with these. So this is still calcite, so be careful with the recognition of feldspars versus carbonate. Use the acid, and this is fizzing, so it's a pink carbonate, so it goes with the calcite. So this is a type of calcite essentially. Instead, this will not fizz with the acid, and included in here, these black minerals are actually biotites. So you can check for the streak color, and it should be brownish, and in fact it is. So brown color or streak will help you with the definition of the type of phyllosilicate. And you can see also the classical pseudo-hexagonal shape, and it's really dark in color, another good indication that you have a biotite. So it's a combination of rocks that combination of minerals, of really two minerals, mostly carbonate and biotite. Here we have a characteristic rock that has these, I would call them Perferoblast. We haven't introduced this term as yet, but often metamorphic rocks contains the equivalent of igneous rocks, so the well-developed larger crystals, which are called phenocrysts in igneous rocks. And this is quite nice because you can clearly see cubes forming these crystals, and that's characteristic cubic symmetry, and the gold color is also indicative of a mineral called Parrot. So Parrot is a very abundant iron sulfide. So we could take this cubic Parrot, and that would be your typical example of that. So I hope you were able to see this section here that is characteristically showing 90 degrees angles between the faces in section of this cube. So that is really a diagnostic feature for Parrot. So hopefully you are able to see that. But yeah, we can also use the USB microscope to illustrate this aspect better. Then we move to the opaque minerals. So we are left mostly with opaque minerals. We will start with this is like transitional between the two. It's this Spinel. So I've mentioned Spinel quite a bit. Remember the symmetry. It's a B pyramid. It's quite dark in color, black actually, and you should be able to see quite well the pyramid if you look carefully at it. And yeah, it's stubby appearance, so still a cubic mineral. You can find these octahedrons also while you are developing Parrot. So the symmetry is very similar for these cubic minerals. So Parrot, garnet, and Spinel are actually all cubic minerals. It's also very hard, so the hardness is very high. Also Parrot is quite hard. In fact, both minerals don't really have major cleavages. Most of the striations you see in Parrot crystals are related to the crystallization of Parrot. And so Spinel is again a cubic mineral like Parrot. Other minerals, we enter the world of sulfides and oxides. So we were dealing with iron and magnesium oxides like Spinel, which can contain also chromium, or Zinccian Spinel may also be present. So it's important to realize the Spinel is a group of minerals. It's similar to garnet. You have different substitutions. This is also partly Parrot, but in this case it's more massive. So it doesn't really appear in euhedral form, but we can still put the Parrot together here. In reality, this sample contains also pyrrhotite, so we have to be very careful and look carefully at the specimen and essentially map the color variation. There are coppery veins in the specimen that are darker and more coppery in color, and then we have more yellow plugs in here, so dark yellow and light yellow. So the light yellow will be Parrot, the dark yellow will be Chalcopyrrot, so copper iron sulfides are present in this rock. Another example of the transition in color is found in this one. So we have the same situation here. You have an aggregate of different minerals. So we have in here the pyrrhotite is mostly abundant, and then we have an infill of Chalcopyrrot, which is this darker yellow goldy color in the center of the specimen. So this will be weakly magnetic, this is non-magnetic, and that's another way in which you can make a distinction. So remember that. And so this is more bronze, coppery in color, this is more goldy in color, and goldy as well. So Parrot is gold color, so the fool's gold, and the pyrrhotite is more bronze and more pinkish, but still metallic. So all these opaque minerals have metallic appearance. You can see a vein here of likely hematite, so I would have to test with the magnet and see if it does stick, and that will help with the identification and distinction between magnetite and hematite, which looks very similar. So you can see I have some magnetite in here for sure. So probably these are magnetite veins, or there might be traces of magnetite together with hematite. How do you recognize the difference? Usually you use a strict plate, and yeah, this is very dark, it's black, so dominantly, at least for this portion of the specimen, this will be magnetite. So we can take the label for magnetite and place it here. We were forgetting this, so let's see if I can find well, Parrot is already there. Yeah, we could take this one and this one. Sometimes Parrot will be together with quartz. It's not this example, but still there is Parrot in here. And pyrrhotite, it's this one here. And muscovite, I think we used that already, but we can put it there so I can reduce the number. Chalcopyrrot, I've mentioned that this specimen contains small chunks, so both of them will contain Chalcopyrrot as well, which is the dark gold. And we can go on. I mean, I'm pretty sure this one doesn't stick to the magnet. Let's see if that's true. Yeah, I don't see any real response. So if the streak color is red and it's deep red, I have two factors that tells me that this is and also this characteristic reddish color, it's quite important because it tells me it's a hematite. This is also a particular variety of hematite. It's called globular hematite. So globular hematite forms these hemispheroids, and it's probably a combination really of oxides, so hematite, and also another hydroxide, which is formed through interaction with weathering and water basically. So this will turn into goethite, so we can have both hematite and goethite present together when you see this characteristic alteration texture. So globular hematite there, streak color, non magnetic, easy to identify. let's test again here. I can see here we have definitely a response of probably a mixture of hematite and magnetite, so this specimen can sit in the middle. This I remember from yesterday. We had quite a bit of response here, so that's definitely your magnetite. These are other specimens, I think, of hematite, more massive, and you can see that it can look very similar. So this is magnetite actually, so that's magnetite, and we take this is more silvery in color, much heavier, and often has 90 degrees angle on the faces, which is indicative of the fact that it's a cubic mineral. It doesn't really display any magnetic properties. In fact, this is a lead sulfide. So your galena is this example. So remember, it's more shiny, and the classical gray of lead sulfide, and you will often find pits in galena that form essentially faces that sit at an angle of 90 degrees. And so that's another indication of cleavage associated with the structure of the galena, that is in this case very similar to the cubic minerals we just reviewed, so the Parrot, for example, or the Spinel, and some of the other oxides as well. So here we have galena, and then we have these last minerals here. So I think this is still, you can see the coppery color, and it should be responsive. You can see this actually magnetic, but more weakly magnetic. So that's your pyrrhotite again. And then we have this other, which is much more shiny, and usually it forms also characteristic cleavages, which gives it this jagged aspect, and you can see brownish and reddish tones as well, and honey colored tones, which are quite diagnostic for a sulfide, and in this case we're talking about sphalerite, so it's zinc sulfide. So your sphalerite usually has adamantine luster, and it's really the result of a substitution between zinc and iron that produce this variation in color that is often observed in the sphalerite. So let's see if I have sphalerite here, and I'm lucky I do have sphalerite, which completes this discussion about the nomenclature of minerals. We also have this. Okay, we can. I had to replace the battery of my camera, but we can continue with this discussion about the nomenclature of minerals. I hope in the final production I'll be able to read these labels. If not, just rely on what I say, and I think it should be enough to understand some of the features of the minerals really, and connect them to the names of the mineral. If you remember, we had plenty of discussion about this greenish mineral, which is pyroxene. So pyroxene has hardness of between 5 and 6, and it does have characteristic cleavage on its basal. So if you can recognize the cleavage, which is at roughly at 90 degrees, you will be able to really tell that this is a pyroxene. So let's see if I have pyroxene. So pyroxene will be, that's the correct term, and we can place the pyroxene in here. We had also other pyroxene, which was this one, and this one. Remember the squared section for the pyroxene, squared as well, although you have now numerous faces as well, but yeah, the major faces are squared also in this crystal. So you do have to look at many things, not a single thing. And then we have our apatite in here, which I might not have a label, but I do actually. So there we go. So we have the apatite. So we mentioned that the basal is hexagonal for the apatite, so you can see the angles, and that's forming an hexagon, and all sort of other features, but certainly the hardness is lower. So we said talc, gypsum, calcite, fluorite and apatite. So the 5 is here, so in theory it's hard to scratch with the pin, which is 4, and in fact it's much harder if compared to the other mineral we were considering before, which I think was either talc or gypsum, which can be scratched by the pin nail. Other minerals that are critical, I think, will be your amphibole. So that's amphibole, and amphibole is somewhat more flattened and elongated, and you have these characteristic striations and the flattened lozenge shape. So you can see a basal in here, which is more flattened, or even this one, it's even better. So quite flattened lozenge, so a flattened section essentially for your amphibole. Remember the cleavage, that it doesn't form 90 degrees, rather a larger angle, so 126 I think, or 28, depending on the amphibole. So that's your amphibole. So the cleavage will be critical for the distinction of amphibole. Here we have a mass of amphibole with different grain size. Really, we have very tiny amphibole crystals and larger crystals with that characteristic lozenge section, so flattened lozenge, forming that angle that is really linked to the cleavage as well. And that's again amphibole, in this case within quartz. This is the super hard hexagonal mineral, the tourmaline. So remember, tourmaline, it's quite hard. It doesn't have clear cleavage because of the hardness. It tends to fracture irregularly, and yeah, it does have this characteristic green as well, and it's extremely hard. So that's a key distinguishing criteria between tourmaline and apatite. I'm gonna put it here. I don't have a label for tourmaline, but remember it's a cyclosilicate of boron. I've got now this one, which is the heavy barium sulfite, so that's barite. So remember, you can scratch it quite easily but it doesn't react to the HCl. We can put it actually close to the carbonates. And so that's your barite. And we complete this survey with the garnet. So I don't have a label for garnet as well, but again, we mentioned that during the lectures quite a bit. So remember, it's quite often a metamorphic mineral, and it's cubic, so it will be well rounded like this crystal. So it's easy to distinguish it because it's very similar to the Parrot dodecahedrons, but of course it's more reddish in color, and the luster is, I would say, close to adamantine, and also it's quite translucent if compared to Parrot, which is non-translucent. And so you cannot really make a mistake between garnet and Parrot. It will be easy to recognize. Also, quite often it's reddish in color, garnet, so you will be able to tell that this is garnet based on that. See how it's glassy in appearance, and it's very hard as well. Pretty much like olivine. We have discussed olivine already. So olivine will also be quite hard, similarly to garnet, but it does have this characteristic olive green color, and that will help you with the identification also of rocks such as peridotites, because it's always common to find dunites that have this appearance. In fact, these are dunites with small crystals of olivine. I think talc is already been classified. Probably the really important ones have been done. We are left, I think the only one that we are missing is the Plagioclase. So let me see if I can find a piece of Plagioclase in here, which I think I'm lucky, because this looks like Plagioclase. So the Plagioclase will be very similar in appearance to your feldspar, so Plagioclase here, orthoclase. So this is still a feldspar. It does have a hardness of 6, but it tends to be very white, and you will still recognize 3 cleavages in the Plagioclase, which can be helpful. You can recognize them because there are parallel sets of fractures, and they often have 90 degrees as well. So this is a hard distinction to make, but many times white feldspar will be Plagioclase, although you can get white K feldspar as well. So let's assume that for the sake of this exercise, this will be definitely your K feldspar, pinkish in color, and this could be either K feldspar or Plagioclase, but most likely Plagioclase. So other diagnostic features for feldspar with respect to comparing it to other specimens like carbonate, let's say we have calcite, it's certainly the hardness, so the Plagioclase will be harder, so more difficult to scratch. So we could try to use the knife, and we see that it's quite difficult to scratch it. Actually, you cannot scratch it, and the feldspar usually scratches the glass. So the calcite will not really scratch glass. So a key distinction is really based on the hardness between feldspars in general and carbonates. So I'm left with graphite and chrysolite, which chrysolite can be put together with serpentine. So it's a variety of magnesium silicates, and graphite, native copper, bornite, and bauxite. Often you have concretional rocks like this that form all these concretions or pisolites, and this is a characteristic indication of weathering. Weathering quite often will remove pretty much everything there is in a sandstone, exception made with aluminum, and so you get deformation of aluminum oxides and hydroxides, which quite commonly are termed bauxites. So the bauxite will be termed like this, bauxite. Remember, it does have this characteristic pisolitic textures many times, and it will contain quite a bit of aluminum, and so that's also mined for aluminum, and these are quite commonly rocks that form in tropical regions, and they are termed laterites. Native copper. So native copper is just the element copper. Sometimes you find it like this, with a very dendritic appearance, and it's of course coppery and very metallic in color, and that will be very easy to differentiate from other minerals. So see, this is included in a rock, and so you can see this dendritic texture with some also alteration, which is quite commonly malachite forming, as well as other copper hydroxides. So that's your native copper, very jagged. The bornite usually has this bluish luminescence. Hopefully you can see this purpley to bluish colors. So the iridescence will be helpful in the identification of this opaque mineral, and that will be, I think, the key way of identifying the mineral. The fact that it's bluish metallic, it's very helpful to detect this copper sulfide. So that's your bornite, and then we are left only with the graphite. Okay, so we were struggling to find the graphite. I have identified a nice specimen of a graphite schist. So in this case, this rock is pretty much all composed of graphite and a little bit of silica, and yeah, its characteristic is luster. So it does have a metallic luster, and of course the streak will be black or dark gray in color. So it's pretty much similar to when you write on paper. So that's your graphite. So it's an opaque mineral, and it doesn't have well evident cleavage, exception made for one cleavage, which is parallel to the foliation of this rock in this particular example. But yeah, you will feel that it's quite greasy, and it will leave your fingers really dirty because of this plane of weakness in terms of its structure. If you remember, it does have van der Waals bonds that separates layers of carbon, which, if I remember correctly, are in hexagonal shape or hexagonal configuration. And so if you apply a stress on this rock, you will exfoliate tiny chunks of carbon, and this is why it's easy to use it for writing. So that's your graphite. Remember, we have native copper here, again jagged and copper in color, metallic, easy to identify, and it doesn't have any cleavage. This is a bauxite, so a rock that is a laterite with a lot of weathering that has essentially removed a lot of the chemical components of the rock, but left behind a lot of aluminum oxide. So bauxite often is found in these pisolithic rocks. So that's another way of distinguishing, and it's often associated with iron oxide as well, which explains this reddish color. So there is quite a bit of hematite associated with this specimen as well. And also the last one was the bornite. So remember, bornite will be bluish, so it will be metallic, has metallic luster, and this bluish color is quite useful for the identification of bornite, which is still a copper sulfide. I think this concludes these other exercise of sort of trying to identify a name for all these minerals with the different characteristics. In the next one, we will focus on simple minerals. I was forgetting actually that I found also this piece of euhedral quartz, which is quite instructive, because it does have this pseudo-hexagonal section, as well as the pyramid that sort of terminates the euhedral crystal. Unfortunately, this is broken, otherwise you will find another pyramid at the bottom. So it's usually a bipyramid with this pseudo-hexagonal symmetry. So that's your euhedral quartz. So it would sit right here with the other quartz that is more massive and doesn't display a euhedral habit. So these would be anhedral, based on the second lab. So when we will talk about different terminology, we'll find out that we can call them anhedral or euhedral if they have a proper shape, or if they don't have proper shape, they will be anhedral. Minerals. So I leave you now, and we can catch up with the exercise on the Bowen sequence.